Okay, now let's take a look at a problem that involves a phase change, which in some cases you may have multiple steps and multiple formulas in which you have to determine a series of answers, and then to get the final answer simply add the four together. So in the spirit of these strategies, let's look at the question. A 100-gram sample of water at 20 degrees Celsius is heated to steam at 125 degrees Celsius. How much heat was absorbed? Okay, we need to analyze this problem. We need to realize that, first of all, there's some phase changes involved. We'll be looking at a graph also to explain those changes that are occurring. Also realize that in this case, you're going from water in its liquid form, because it's at 20 degrees Celsius, and then undergoing a phase change to steam, or a gaseous or vapor state, at 125 degrees Celsius. So let's record. In the given information, this is what we know. We know we have the temperature of water, 20.0 degrees Celsius. We know we have the temperature of steam, be 125 degrees Celsius. And we know that we have a mass of water that includes 100 grams. Okay, all right, let's take a look at the graph. This graph represents a relationship between energy and the temperature of a substance. Each of these straight lines in the graph represents no temperature change. In this particular case, temperature is on the y-axis and the amount of heat input is on the x-axis. So you have no change in y, therefore you have no change in temperature during these two areas of the graph. This is the phase change part, because if you remember from your reading, there is no change in temperature during a phase change, and this is indicative of that. All right, so realize that we are, if that is 0 for the phase change from a solid to a liquid, this is 0 degrees Celsius. Of course, we're talking about water. And then this is the phase change from a liquid to a gas, and that temperature would be 100 degrees Celsius. Somewhere in this area right here is where we're starting in this problem. We're ending in this problem somewhere at 125 degrees Celsius, so we're above the phase change. So we're still analyzing the problem. In this particular case, you're changing liquid water from 20 degrees Celsius to 100 degrees Celsius. And that's going to involve a formula for heat equals the mass times the specific heat times the change in temperature. We'll write it in a minute. That's going to involve that formula. And then you're going to have to incorporate the heat of vaporization formula, because it's changing phase from a liquid to a vapor. Q equals mass times the latent heat of vaporization. And then finally, once it turns to a gas, we'll go back to the Q equals mCT formula, because now it is again changing its temperature. All right, so let's write down all these formulas. Okay, we have 3. First of all, we're taking it from Q, M, C, delta T. The second formula is Q, M, times the latent heat of vaporization, M of course representing mass. And then the final formula is Q equals MC delta T. Remember that M represents the mass, C represents the specific heat, and then the delta T represents the change in temperature. M representing mass, L sub V representing the latent heat of vaporization, and then the same formula as the first here. So now let's substitute into the first formula, Q equals MC delta T. From the given information, you're changing 100 grams of water for the mass. It is a liquid, and the specific heat of water in its liquid form is 1.00 calories per gram degree Celsius. And then we're multiplying that times how much it changes temperature. Within the liquid part of the step, it's changing from 20 degrees Celsius to 100 degrees Celsius. So therefore its change in temperature is 80 degrees Celsius. Okay, math should be pretty simple here. We've got 100 grams times 1 times 80. That should give us 8,000. It appears that we have three significant figures. So we'll put a line over that 0 to represent three significant figures in 8,000. And the unit that would remain would be calories. All right, so this we'll just call this 1 because that's our first formula. Q2 is going to be the phase change part. Mass times the latent heat of vaporization. The mass hasn't changed. You still have 100 grams, and we're multiplying that times the latent heat of vaporization, and the substance is water. And according to your textbook, 540 calories per gram is the amount of energy required to change the phase of water from a liquid to a gas. And again, math is pretty straightforward, so that would be 54,000 grams cancel. The remaining unit would be calories, and in this case the number of significant figures would be 4. So Q2 is equal to 54,000 calories. This means that it requires 54,000 calories of energy to change the phase of the water from a liquid to a gas. Now, let's go for Q3. Again, it's MC delta T because we're back to changing temperature again. The substance of the water in this case is now a gas. It is still 100 grams. And then the specific heat of gas, according to your textbook, is 0.480 calories per gram degree Celsius. And we're changing the temperature from 100 to 125, so therefore there's a 25 degree temperature difference. 100 grams times 0.48 times 25 degree temperature difference. It's going to give us a nice even round number of 1,200. And now let's determine the number of significant figures. It'd be 4 there, 3 here, and 3 there. So we'll have 3 significant figures, and the unit again would be calories. So our Q3 would be 1,200. Let's revisit the chart, remembering that we started at 20 degrees Celsius, went to 100, and the amount of heat energy required to take it from 20 degrees Celsius to 100 degrees Celsius while still being a liquid was 8,000 calories. So this essentially is Q1. Then the amount of energy required to go from a liquid at 100 degrees Celsius to gas at 100 degrees Celsius, Q2, is 54,000 calories. And then finally, the third formula, Q3, is the amount of energy required to raise the temperature of 100 grams of water in its gaseous state from 100 degrees Celsius to 125 degrees Celsius, and that value was 1,200 calories. So the total amount of energy required to go from 20 degrees Celsius as a liquid to 125 degrees Celsius in a gaseous state would then be determined by taking the sum of Q1, Q2, and Q3. So to determine the total amount of heat energy required, Q total is going to be Q1 plus Q2 plus Q3, while Q1 was 8,000 calories with last significant digit being in the tens place, Q2 being 54,000 calories, last significant digit being in the tens place also, plus Q3, which is 1,200 calories, and again the last significant digit being in the tens place. So when we add these three together, $8,000 plus 54,000 plus 1,200, we get 63,200 calories of energy, with the last significant digit being in the tens place, because remember that's the least certain of any of the three, because we added according to the rules for significant figures. So final answer, Q total for this problem is 63,200 calories. Because it's such a large number, you may actually want to represent that in kilocalories. It could be expressed as 63.20 kcals. Hopefully that helps.